thanks for inviting me to talk in this workshop. So my name is Tuomas Koskela, and I'm a research software developer at UCL, and I've been working very closely with Serge and Alex and others to develop this software that you just saw some results from. And my talk is going to be on implementation rather than results, which Serge mentioned in the beginning. But so I'll try to talk quickly about sort of the HPC side of this project. So what happens when you need much more than 100 particles and you can't run these simulations on your laptop anymore? So what kind of challenges does that introduce? So I'm sorry, let me move things around a bit. Right, so the H part of RADDISH is on HPC, and so the goals of the project were to couple agent-based models with physics-based tsunami models and develop fast implementations of state-of-the-art data assimilation code targeted at HPC. And here I've sort of highlighted the parts that are of most interest to myself and this talk. So implementations of particle filters that are fast and can run on HPC systems. What do those look like? And for this project, we've developed a software package called particleda.jl. You can find it on GitHub, and we've tried to follow some good practices on how to develop sustainable software. So what the package does is it has an interface for implementing arbitrary forecast models. So it's like a particle DA package where you plug in your model, which can be, for example, the model Alex talked about, which is this a simple linear shallow water equations on a linear grid, rectangular grid with synthetic observations. But there's some work in progress to include more complex models for more realistic simulations. And then there's implementations of particle filters. So we've implemented the two filters that Alex mentioned in his talk. So the bootstrap particle filter, which is very simple. You just take the output of your model, add some noise, and move on to the next step. And the optimal filter, which just something a bit more sophisticated. So a bit about the technologies involved here. So like I mentioned, we've developed the code on GitHub and used, so there's been a collaboration with few people. So and using GitHub is very good because it allows you to review code, submit issues, and discuss features. We've been taking heavy advantage of GitHub Actions in doing continuous integration, discovering bugs, and also following the impact of our changes on the performance of the code. Like you may have noticed from the extension of the name on the package, we're using the Julia programming language, which is a fairly new technology, but that has matured a lot recently and has been very useful in this project as a sort of tool for writing efficient HPC code that still is fairly friendly for developers to work with and hopefully for users to understand as well. The sort of HPC technologies doing the heavy lifting for us are so MPI we're using for the parallelism. It's an old technology, but it still works and it is available everywhere pretty much. And HDF5, which is a file storage technology. So we get a very nice sort of structured files for our output. So this is sort of my naive understanding of the particle filter algorithm, what needs to be implemented in the software. So if you start at the top, we're updating particle states using our forecast model. Then we update the particle proposal that we're going to pass through the filter, and that can be just the states or something else. We collect some observations at some discrete points in our domain. We collect those same observations from our particle states. We calculate weights for the particles. We resample the particles, and here typically also produce some diagnostic output, like statistics, for example, on how our simulation is running, and then we go back to the beginning. So from an implementation point of view, this is nice because all the communication you need to do between your parallel processes happens in this resampling step, and everything else you can just forget about, that you're running a big ensemble, and just update each particle at the time. So our approach has been a combination of shared and distributed parallelism because of this. So basically what you want to do is split up your particles between your ranks of MPI, so between your distributed processors. And this means that basically you don't increase your memory use per rank when you scale up. You just add more processes and fill up their memory, and you can go almost as high as you like. And it also means that the cost increase in the dimension of your state vector is roughly linear in the particle updates, and it brings some cost in the communication phase, but I'll come back to that in a moment. So then the shared parallelism, you can use threads for particles that live on the same MPI rank, and this Julia has a very nice interface for doing using a macro. So you just decorate your loops that you want parallelized with this macro, and give it some threads, and off it goes and parallelizes. And then when you need data to collect data from all your particles, which is basically at the resampling state, then you have to use some MPI communications, and we're using a Julia package for MPI, which is just like a very shallow wrapper over the C MPI library. And this will almost always be the performance bottleneck once you start scaling up the MPI communication, just something to keep in mind. So, okay, so I have a very simple cartoon of how the communication looks like. So I have a 4 ranks here that are updating the particle state, and this can use threads to parallelize, and then calculating the weights of their local particle ensemble. Then we don't need to communicate the particles, but we need to communicate the weights to one process that can do the resampling. So calculate which particles we eliminate, which ones we replicate. And then this information needs to go out again to all the ranks. And then follows this tangle of copying data from one rank to the other. And this is basically where all the problems come from. If there is a lot of degeneracy in the particles, then this will look very unbalanced, and that will be very slow. And then in the end, to get some statistics out, so we've been calculating means and variances, you need to do a reduction again over all your resampled particles. This can also be a bit heavy once you're running at high parallelism. So hope that made some sense. Here's an example, some example data we ran on the Cambridge CSD3 cluster. We used the Knight's Landing partition, but that's not super important here. This will run on just as well on any CPU partition. We used a Julia version 1.4, which is now already a bit old, and we're up to 1.6. So the nice thing about KNLs is that you have a lot of you can run a lot of threads per node. So we were running 16 threads on each MPI rank and 64 particles on each thread and 4 ranks on each node. So if you do the math in your head, you get some numbers here at the bottom. So at the right hand side of this plot, we're running over 250,000 particles in parallel. And this plot is showing the parallel efficiency. So how much performance you're losing compared to how well your single, like how well they would run on a single, like how well the work that you're giving on a single process would run if you only had that single process. I hope that made some sense. So essentially, if you're scaling perfectly, you would have a flat line at 1, and we're going, when we're up to 256 MPI ranks, we've lost about 10% of performance, which is not too bad. And if you are interested in where this performance loss is coming from, it's coming from this MPI collective communications. So here's a breakdown of some of the most main bits of the code. And so you can see in blue the particle state update sorry, so the y-axis here is now the runtime and not the efficiency, but you still want to see flat curves. So the particle state update is doing very well. The process noise, which is the proposal update, is also parallelizing very well. And the things that go up as you go up in number of ranks are this MPI gather operation, which is gathering the weights, and then the calculation of the mean and the variance. So some sort of lessons we learned over the course of this project is continuous integration is super useful. So it's helped us catch a lot of problems early and like made our development cycles very fast. And you can also use it for performance, which is nice. So you immediately see if the optimization you did was effective or not. Yeah, when you're developing parallel code, testing in parallel is important because otherwise you miss interesting bugs. So Julia is very nice because there's a large package ecosystem of open source libraries that are very easy to include in your own work. So definitely make use of those whenever they exist. You may raise the question of why are we developing a new package? Isn't there one that does this already? And that is not a bad question, but we couldn't find one that was focused on parallel performance as much as we wanted to, and that's why we decided to develop our own. So clear interfaces between different parts of your software for it. So for example, in our case, between the forward model and the filter are important so that you can plug in different versions that someone wants to try out. Sort of in terms of performance, avoiding all sorts of temporary variable allocations is extremely important, and load balance can kill your performance if you're not careful. So the particle filter is interesting in the sense that the parallel performance of the software is coupled to how correct or like how well the filter is doing. So if you're getting the right result, you will get it very quickly. If you're getting the wrong result, you will get it very slowly, which is like took me a while to wrap my head around. I want to finish by showing a few visualization examples that you've already seen in the talks. So we have some notebooks that do some visualization based on the HDF5 files that we produce. Some in Jupyter, and then we've been working recently on something called Pluto, which is a reactive notebook environment in Julia, and contributions to these are very welcome because we don't really know what other things you may want to visualize in this filter. So I'll just finish with a quick video of how our Pluto notebook works. So you get some contour plots here at the bottom, like Alex showed. So you have the true height on the left and the assimilated height on the right. And now, because Pluto is reactive, you can update the value of the time step, and it will update the plots online. So this is very nice if you want to sort of scroll through your simulation and see what's happening, and then decide where to look for in more detail. If you scroll down here a bit, there's also scatter plots of there it goes. Some scatter plots of how the weights of the particles are behaving, and these will update as well. And yeah, then we have some static time series of here's the estimated sample size, and you can also put this whole thing as an animation and see how, and save it in a video file and show in presentations.
Thank you.
Thanks. And yeah, I think that's all. Okay, video's done. Okay, yeah, so briefly about the future for this software, I'm hoping is to couple
1 minute, half a minute, please, because we are.
Okay,
yeah.
Future plan is to couple with more advanced tsunami solvers and do some more realistic simulations. Thank you.